tonight's talk.
Great. Do you want me to start now? Okay. Hey, thanks for coming, everybody tonight. And it's a talk about life in the solar system tonight, or more precisely, the potential for life in the solar system. So, not that kind of life. Somebody might know Pore from a movie a few years ago, and Alf from more than just a few years ago. That was a TV series, which was really quite a funny thing. More like the tiny microbe life that we'll be looking at, and maybe something a little bit bigger. These are some of the weird-looking life that we've actually found in Earth's oceans. So I've divided the talk tonight into the following sections there. We're going to talk about what is life and have a little bit of a look at life on Earth. Then I want to move on to building blocks of life. What's life made out of, and where do we find these building blocks? And then have a look at the question, how might life get started? That'll be followed by extremophiles, which are life forms on Earth anyway that love to live in very extreme conditions. Following that, we'll move on to habitable zones, and then we'll look at habitability in the solar system. I'll start that one with Enceladus tonight, and then next week we'll have a look at Europa.
Next week and
next month actually, won't it? Yeah, I won't be that quick. Next month. Titan and Mars. I'm getting too excited there. So first of all, a couple of did you know facts here. Now, you may not know that Mars used to have a substantial ocean which covered about 20% of its surface and lasted about 1.5 to 2 billion years. It actually had more water than Earth's Arctic Ocean. There may be 14 oceans in our solar system currently. That's including Earth, 12 moons, and possibly even Pluto. There are microbes that actually eat electrons or electricity, and also that produce electricity. And all the components of DNA and RNA have been found on meteorites except for deoxyribose, which is the D of DNA. And that means that most of these must be formed throughout the solar system, the galaxy, and the universe. So we'll talk about some of these things tonight and next month for some of the rest of it. So since this is a talk about life in the solar system, we want to ask the question, what is life? These are just some of the attributes that people have used to try to put together in an effort to define life. And one of the ones that a lot of you might remember is Mrs. Green from high school, which is movement, respiration, sensitivity, growth, reproduction, excretion, and nutrition. But like a lot of definitions, this has a few problems. For example, a mule is a living thing, it's alive, but they don't reproduce. And how much does lichen on a rock really move? That's a living thing as well. And in fact, this one, Mrs. Green, could probably apply to fire just as well, if not better than some life forms. So trying to define life is not an easy thing. And there are over 100 different definitions of life, each with little differences, slight differences between them. Most of them need to be qualified with exceptions, and very difficult to apply to life that we just don't know anything about, so totally unknown life. And scientists and philosophers have even said things like you can't rigorously define life, and it's a mistake to even try to define life. So essentially saying don't bother. It's kind of, you'll know it when you see it kind of a thing. But we do know a little bit, obviously, about Earth life, and well, mainly about what it's made out of, and we know we need water. Earth life is carbon-based. It all uses DNA, RNA, it has cells, and it uses a molecule called ATP, adenosine triphosphate, for energy. And that applies to all life on Earth. It excludes viruses, and whether a virus is alive or not depends on who you talk to. Probably about 25% of people might say they are alive, 25% will say they're just a little very complex molecule. And so it's not really agreed upon when it comes to viruses. So if we look at Earth life, no matter how weird it might look, we can find that all these are made of cells and contain DNA, RNA, and use that energy molecule ATP. Those are actually slime molds, those two. And that's a thing called a siphonophore. That's about 100 meters long. It's just like a string of little animal units called zooids. This one here looks like a rock, but it's got lichen on it. And these are just some weird sea creatures that have been found. That one looks like just like a plastic bag. And that's just some of the weird stuff that we have. And as I mentioned before, viruses don't have cells, don't use ATP. Some have RNA, but not DNA. And so it's a bit debatable or comes down to preferences to whether people think a virus is a living thing. But there might be other types of life as well. Maybe hydrocarbon life, maybe it might use methane, ethane or octane instead of water. Maybe even be non-cellular. Similar with maybe liquid nitrogen, something that lives in liquid nitrogen. And the reason that these two may be non-cellular is because these would be very, very cold environments and reactions would happen very slowly. In that case, a cell membrane might actually slow things down so much that the life would just give up and die because nothing much would be able to happen, and so it may actually be better off without a cell. And we continue on to things we maybe can't even imagine, so a question mark is the best thing to put on that one. But then again, if we talk about non-cellular life, then we have to start giving viruses a chance, so things get fairly messy in the definitions of life. So let's start with life on Earth, the one we kind of know a little bit about. Now you may or may not know that there are three domains of life on Earth: the bacteria, the archaea, and eukaryotes. Humans, along with actually slime molds, fungus, plants, and various other things, are eukaryotes. The other two, bacteria and archaea, are called prokaryotes. They are all single-celled creatures, and these two actually used to be lumped into one just called bacteria, but it was found that there's substantial differences in the cell membrane between the two, so the archaea are no longer considered bacteria but have their own domain. And just quickly, the differences here are that eukaryotes have a cell nucleus which contains the DNA and has these little things called mitochondria for the powerhouse of the cell. The archaea and bacteria just have their DNA floating around in the cell without a cell nucleus, and they don't have mitochondria. And then the difference between these two is in the cell membrane. The cell membrane of bacteria and eukaryotes uses fatty acids, but the archaea use something a bit different. It uses something called isoprene molecules, chains of isoprene molecules, which actually allowed some of these to live in water that's well over 100 degrees Celsius. And so some of these can survive up to 130 degrees, which is getting pretty hot. And the archaea are also the domain which contains the methanogens, which are methane-producing microbes. Now, if we trace these back using RNA, we come to this thing here called LUCA, which is the last universal common ancestor. And so it works out that biologists can trace back and find that there must have been this thing called LUCA, which would have been probably a methanogen. The archaea are the most archaic, I suppose, are the most primitive of the three. So LUCA would have been a methanogen and also a hypothermophile, which means it would have lived in very hot water. And if we go back a bit further, of course, we must start with chemistry and then something called replicating systems chemistry, which is chemistry where molecules kind of replicate themselves through various reactions. Then we get to a pre-RNA world, up to an RNA world, so that's the world where we have the RNA molecules, but no DNA or protein, and eventually up to DNA, protein, and LUCA. So that's just a bit of a very rough overview of domains of life and a bit of history there.
Excuse me, what's LUCA?
LUCA is the last universal common ancestor. So tracing back through RNA, they come up with what must have been the the common ancestor of all these life forms. Before that, there was probably some other things that branched off and disappeared, but these are the ones. This is the one that probably was the ancestor of these common life forms.
I think eukaryotes are thought to be a symbiosis between archaea and bacteria.
Yeah.
So the mitochondria are actually
Bacteria.
descended from bacteria.
And
chloroplasts, which plants have, are descended of a different type of bacteria.
Yeah, it's quite amazing, isn't it?
In the symbiosis to form a new cell type.
Yeah. And it's quite amazing because they are very similar to bacteria, those mitochondria. And so, so back in the past, they kind of joined together. And so eukaryotes actually appeared about 2.7 billion years ago, about a billion years after these. So a bit of time there for them to kind of join up and continue that way. That's a really interesting point, actually. And I talked about extremophiles before, so let's just have a quick look at what these are. As I mentioned, extremophiles are things that really sometimes even require extreme conditions. And some of them actually wouldn't survive in in non-extreme conditions. So if we look at this one up here, for example, it survives up to 130 degrees and lives kind of in the 80s and above. If it was down at what we call a comfortable temperature, it would die of cold. So to that, we're probably the extremophiles. And then we go to the colder living creatures and even radiation immune kind of microbes. I'll show you on the next slide a bit more about those. And as I mentioned before, Luca was thought to be an extremophile, and that means that life could actually adapt to the very extreme conditions very early on in its appearance on a planet or a moon, which will be interesting when we have a look at some other locations in the solar system. So if I just go a bit more into these extremophiles here, this is Methanopyrus candeleri, which is an archaea, and that one lives happily at 122 degrees and has been seen to survive up to 130. That's actually called a hyperthermophile because it's more than just a thermophile. It actually prefers more than 80 degrees. And at the other end of the temperature scale are the cryophiles. This one here, Planococcus halocryophilus, is a bacteria which is quite comfortable at minus 16 degrees Celsius, which obviously we'd find extremely uncomfortable. And it's been seen to be functional right down to at least minus 25 degrees. And it was found in the Arctic permafrost. This one's also actually called a halophile, which it's actually means it's quite happy with salty conditions. This one up to about 20% salt. Our oceans, for comparison, are about 3.5% salt. And the other really interesting one are the radiophiles. This one here, it's Deinococcus radiodurans, is another bacteria. This one is comfortable at something called 60 grays per hour. Now, a gray is a measure of the amount of radiation absorption, joules per kilogram. And to give you an idea of how bad a gray is, a human would die about 8 or 9 grays. This can survive up to 15,000. So that's, when you think, just 8 or 9, less than 10 for us. This one's comfortable at 60 grays per hour and has been seen to survive up to 15,000. So you can imagine somewhere near Jupiter where there's a lot of radiation, that there could be something which might actually be okay with that kind of thing. And this one is also resistant to various acids and chemicals. It's okay with cold, vacuum, dehydration. And these two are not just extremophiles, they call these polyextremophiles, which means they can survive in more than one type of extreme condition. And here's just a quick list of some other possibilities. We saw the thermophiles and cryophiles and the radiophiles, and we had a quick look at halophiles. Some of these are okay up to about 37% salt. I think that's more than the Dead Sea. And acid, alkaline, pressure, arid conditions, and I mentioned, I'll just go through there, I mentioned the polyextremophiles as well, which can survive various combinations. In fact, most extremophiles are polyextremophiles. And on the other side there, just a quick look at some of the energy sources for microbes. This one here is interesting. If you know, some of you might know that the surface of Mars has a lot of this stuff called perchlorate, which is a very poisonous kind of a salt. There have been bacteria which have been put into environments on Earth, just testing with perchlorate and carbon monoxide. So they eat perchlorate, breathe carbon monoxide and produce carbon dioxide and chlorate. So you can see that gives a bit of hope for something on Mars, even in today's very tough conditions up there on Mars. And I mentioned before these electrotrophs and electrogens. And I think these are really interesting. If you see these two here, these have these little nanowires coming out from them, which actually are used for transporting electrons. So these things eat electrons and send them out the other side. These ones, in fact, if they are put in an environment with no other food, they'll just go and find something which can produce electrons. They've even put them in situations where they put electrodes in water and they've just gone over there and just sucked the electrons off and just been happily eating those. And this one here is even weirder. This is a cable bacteria, a whole lot of cells together which can transmit electricity right through itself like a cable from one end to another. So you just wonder how much, how weird a life maybe they actually get on Earth or even out in the solar system or the universe. So we've had a quick look at what life is and also life on Earth. So now we just want to have a look at the building blocks of life. What are they and where can we find them? Mainly the building blocks of Earth life. So a very simplified bacterial cell having a cell membrane which is made out of these molecules called phospholipids and containing DNA and RNA, and using this molecule here I talked about before, the adenosine triphosphate, or the energy molecule. So let's have a little bit more of a look at where this comes from. And we really have to get right down to the atomic level to really understand where these building blocks come from. There are just over 100 naturally occurring elements in the universe. These are the 10 most common, and down here at number 17 is phosphorus, which you'll see in a moment why that's been included. So out of all the atoms in the universe, just about 93% are hydrogen, about 7% helium, then it drops quite drastically down to less than 0.1%. You might have heard that hydrogen is 75% and helium 25%, and that's true if you're looking at the mass, because helium is 4 times the mass of hydrogen. So if you're just talking about kilograms, it would be about 75% hydrogen and about 25% helium, but the number of atoms is 93, 7, and these little small numbers from here. So straight away you can see why it's quite handy for us that hydrogen and oxygen are in the top 3 atoms in the universe for water, of course, H2O, and oxygen, O2, that we breathe, and carbon dioxide being number 4 for plants. And the reason I showed you those top 10 and the number 17 is because the 6 most important elements for life are these ones: hydrogen, oxygen, carbon, nitrogen, sulfur, and phosphorus. You can think of these a bit like building blocks. We give it the mnemonic CHNOPS just to make it easier to remember. And you can just think of these almost like little Lego blocks, put them together one at a time to make larger building blocks. So if we have a look at an example of how we can put these together, and we just jump to the next slide there. So if we take our carbon blocks, and then we take some nitrogen and then some hydrogen, stick them all together, again just like building with Lego, we've made ourselves a molecule. This one is called adenine. This one in particular is a nuclear base. It's part of DNA and RNA, and it's used also in the ATP molecule. And a quick second example quickly: take some carbon, take some oxygen, and take some hydrogen, put those together, and we have a sugar molecule, this one called ribose. Ribose is the R of RNA, ribonucleic acid. So these two, as you probably saw earlier, have been found on meteorites. And we can go on building our larger building blocks, such as adenine, cytosine, over to here some more sugars, and phosphate, amino acids, fatty acids. And the next interesting question is, which of these have been found on meteorites? So which of these can be made in space? Well, here's three samples of meteorites, and on these, all of them highlighted in yellow have been found on meteorites. So deoxyribose is the only one that hasn't been found, hasn't been made in space yet. Deoxyribose is ribose with one less oxygen atom, so it's kind of been deoxied. That's probably a way to remember what's happened there. It's just got one less oxygen atom. So yeah, all of these found in space. So even some more nuclear bases that we don't use, a lot more amino acids that we don't use. And these are pieces of these three meteorites. Murchison meteorite, which was found in Australia, Lake Murray in the States, and this Tagish Lake meteorite just fell, I think it was about the year 2000, in British Columbia in Canada. So now that we've seen these building blocks, what are they actually useful for? Well, these are the 5 nuclear bases which make up the rungs of DNA and RNA. Ribose and phosphate make up the backbone of RNA, and deoxyribose, which I mentioned hasn't been found on meteorites, but deoxyribose and phosphate make up the backbone of DNA. Adenine, ribose and phosphate also make this energy molecule. Fatty acids, phosphate, and this thing, ethanolamine, makes up our phospholipids for our cell membranes. And as I mentioned before, the fatty acids are used for bacteria and eukaryotes, but the archaea use isoprenoids. And of course, amino acids, all been found on meteorites, and they make up our proteins and our enzymes. Now, the fact that these have all been made in space doesn't mean that Earth life or life on planets had to use the components from space. It really just shows that they're commonly formed, and they're probably throughout the solar system, throughout the galaxy, and even throughout the universe. So we start off with our chinops elements, make these larger things in space or on Earth, and then they're put together, or they come together, react to form these larger building blocks of life. It's possible that life in other worlds may put them together in different ways, that for example, this adenosine triphosphate here may use another of these molecules instead of adenine. So Earth life is used at this particular way anyway. Deoxyribose might be formed in space as well. Hopefully we'll find it at some stage. Some of these have also been seen on comets too, by just by imaging them using spectroscopy.
When you say they're made in space...
Oh, made in space. Yeah.
Can you explain that?
Yeah, so what happens is that in deep space, in molecular clouds, the ultraviolet light from stars can cause them various atoms or various other molecules to be pulled apart. They can land on bits of dust, and then reactions can occur on the dust, forming these molecules. And so they just generally form quite easily by reactions with... it's mainly on dust, I think. I guess they kind of need to surface, really. Kind of to surface something for the atoms to do their thing and react.
And would the meteorites pick up that dust?
Yeah, so there's a couple of different ways. Like in the clouds, they collapse to form stars and solar systems. So a lot of it would kind of collapse that way. But also, you're right, meteorites and comets moving through would pick up bits and pieces. And it would actually appear that these are just everywhere ubiquitous throughout the whole universe. And so, yeah, so they're just really very obviously easy to form, which is, oh, yes.
So are there any meteorites found from comets?
Meteorites often are chips off asteroids, so we have the asteroids, which are mainly rocky, and then we have the comets, which are mainly icy, maybe with a bit of dirt and stuff in the middle, and they, as you know, when they get close to the sun. And we've also got something called the Kuiper Belt too, which is further out in the solar system, which is where some of our comets come from, and some of those are quite red in colour, which means they've actually got a lot of organic molecules. Methane, probably more orangey. When people say red in astronomy, it's usually orange. A lot of organic molecules on them as well. So even in space, these things tend to come together and form larger molecules, things like benzene molecules, and longer, I guess that's the fatty acid molecules as well. So how might life get started? Now that we know about the building blocks of life, it's important to know where life might get started as well. So apart from panspermia, which essentially is life hitching a ride on a meteorite and catching a ride to another place in a solar system, if there's no way for life to get started, we're not going to have much chance of life in other worlds. So you've probably heard of the warm pond or hot spring idea for a place for life to get started. The first one on the left here, we're looking at tidal pools. The idea of the tidal pool is that tide comes in, fills in a tidal pool. Molecules in the pool will be concentrated together as the tide goes out and the pool evaporates. And reactions are more likely to occur, of course, if you've got your atoms and molecules concentrated together. And the tide comes in again, fills it up, mixes it up, and over, so it's called a wet and dry cycle. You can imagine over millions of years just what could happen. In some places nothing probably happens. In many pools larger molecules will form. And the same idea around hot springs as well. So hot springs with the hot water around volcanic areas, wetting and drying as the water evaporates, gets refilled through the springs. So that's kind of the warm pond or the pond idea of how life may have got started, or some of the larger molecules may have formed. There are some thoughts though that because in the early Earth the moon was a lot closer to the Earth, I think about 16 times as close from memory, that the tides would have been much higher. The Earth would have been, the moon would have been orbiting much faster, so the high and low tides would have been a lot quicker. That may have meant in a lot of cases that the ponds wouldn't have had time to dry out. And so, not saying that it would mean it can't happen there, but may have been a slight impedance there for things to happen. And maybe similar with the number of meteorites landing on the Earth. There are a lot more meteorites in the solar system, in the early solar system. That may have disrupted things as well, possibly, maybe not. But there is another option. If for some reason that was a problem and wasn't how life got started, there's another idea that is quite popular as well. You may have heard of hydrothermal vents. This one on here is a black smoker, and over here we've got a white smoker. These are undersea vents which occur near volcanic areas. Water goes under the sea floor, gets heated up on magma, reacts and comes back up. These ones up to about 400 degrees Celsius, very hot. The white smokers, for some reason, a little bit cooler, up to about 300 degrees, but still extremely hot. The colour is dependent on the minerals that are coming up. Iron sulfide is black, so there'd be a lot of iron sulfide in those ones, and a lot of calcium, barium, I think silicon coming up in these white smokers. Those temperatures there are probably too hot for any sort of life to form, and although these will be very good for feeding life that didn't get too close, there is a third type of vent as well, and that is the alkaline hydrothermal vent. This particular one is from the Lost City hydrothermal field, which was discovered in the year 2000 in the mid-Atlantic, this particular one. These things, the alkaline hydrothermal vents, have water coming through the chimneys that are between about 40 and 90 degrees Celsius, so a little bit lower than boiling temperature. And this particular one here is the field. It's about 500 square meters, I think. And some of these are up to 60 meters high, which is getting to about the height of a 20-story building. So you can see when they were discovered why they would have called it a lost city, because you imagine just finding these things, 20-story high structures under the water. And this one here it's still going. It's probably about 120,000 years old. There are a few others around the world as well. There's some up in Iceland, because I have to remember Greenland is the icy one and Iceland is the green one. So up in this area there's some more, and also some around the other side of the world as well. So how do these things work? What happens here is that no volcanic activity is necessary for these ones. Seawater seeps down into the rocky seafloor. It reacts with a mineral called olivine. This is an olivine mineral in a rock called peridotite. That will form something called serpentinite, another rock over here. So the process down here is called serpentinization. It's called serpentinite because it's green, like a serpent apparently. So this is something called an exothermic reaction, which means the reaction just produces heat. So it doesn't need the volcanic activity. And it produces heat, so it heats up the water. The hot water comes back up with various minerals with it, calcium carbonate, hydrogen and methane, which are produced in the reaction, and various other minerals. And the calcium carbonate produces or builds these chimneys, which eventually grow to these incredible heights. Now, the ancient sea on Earth was actually quite high in CO2, which made it mildly acidic. So this fluid that's coming up through the vents is quite alkaline, meeting seawater that was mildly acidic. And so what does that mean? Well, if we zoom inside these vents, so first of all to 100 micrometers, and then even smaller down to about 10 micrometers, we find these little inorganic pores, which just happen to be about the size of an organic cell. And if we have a quick look at a cell, here's again a simple bacterial cell. Inside the cell we have something called cytoplasm, which is slightly alkaline, separated with a cell membrane from a slightly more acidic mixture outside. Now, that creates something called a proton gradient, which simply means that these little H pluses, that's hydrogen without an electron, it's just a proton. And the proton gradient means that there's kind of more of a positive charge outside and not so much of a positive charge inside. This actually, in living cells, creates a voltage of about 100 millivolts, give or take quite a bit depending on circumstances. And to keep this hydrogen, this proton gradient, the cell will actually pump out hydrogen ions from the centre. So that's a very basic idea of the cell there with this thing called the proton gradient. Now you can see now with these hydrothermal vents, with the alkaline fluid going into these cells, or into these inorganic pores, which are about the size of a cell, the acidic seawater outside is calculated to be about the same, about 100 millivolts or so, give or take. And you can see that as the alkaline fluid comes through, it would wash out any extra protons through the hole, so it's almost like our proton pump. So we've got our gradient here, we've got our proton pump, our difference in voltage. And the other amazing thing about these is the walls here are made out of various minerals which are great for catalyzing reactions. So molecules which find their way in, stick to the sides, and reactions occur more readily because they're more concentrated. So it's thought that this obviously could be quite a good protocell, so to speak. and that life may have started off in these kind of situations, maybe as well as the ponds on the surface, or maybe instead of, but it gives another option as well. But you can see that these are so similar in so many ways that it makes sense that eventually maybe some life could start there. Well, very basic life, pre-RNA type of life. And so just from that, in summary, this is alkaline hydrothermal vent pores would be a very good candidate for a precursor to the prokaryotic cells. And so now what we've found is we have building blocks that seem to be easy to make, seem to be all through the universe. We've seen some ways that life might get started, some options. No one's certain of which way at the moment, but there's certainly some good options there. And we've seen some examples of life that seem to be very happy in very extreme environments, including the last universal common ancestor, something that appeared very early on in the history of the Earth. So of course now we'd need somewhere for life to start and to thrive. And that brings us to habitable zones. Generally regions around a star where some sort of liquid can exist on the surface of a planet, or even under the ice of a moon. So let's have a quick look at those now. So this is the traditional habitable zone, which is the region from a star where liquid water could exist on the surface of a planet. It also requires that planet to have an atmosphere, of course, with enough pressure to keep the water as a liquid. Without a decent atmosphere, such as on Mars, as we see, Mars has lost its oceans, lost its water, because it doesn't have an atmosphere to hold it in the liquid state. And just looking at this thing called a phase diagram of water, you can see the lower pressure we get, the lower temperature, the ice can actually turn straight to gas and miss the liquid phase altogether. And so the boiling point of water depends on the pressure. Right here on the surface of the Earth, we're what they call 1 atmosphere, and so water boils at 100 degrees, but decreasing the pressure, as you know, going up in a mountain, the boiling temperature decreases. And so this habitable zone here, the traditional zone, does require also an atmosphere for surface water. But there's also a liquid methane habitable zone. This is similar to the water zone, but obviously a lot cooler, where liquid methane can exist on the surface of a moon or a planet, generally a moon, as long as that body has an atmosphere with enough pressure. In our solar system, this zone is kind of around the Saturn area. And a good example, if you've seen it, which we'll have a look at next month, is Titan, which has liquid methane oceans, seas and rivers, not quite ocean size, on its surface. But that's not the only habitable zones. There's also now, that's just showing methane is also a similar diagram to water, where it has the gas, liquid and solid phase, depending on the temperature and pressure. But we also have something called the tidal heating habitable zone. And that is the zone around a large planet where a moon, a very icy moon, can have a liquid ocean underneath the surface, underneath the icy surface. This is generally because the orbit is not quite circular, so the moon is getting squeezed and stretched as it moves around the planet, and it keeps the interior warm and allows for an ocean to be present. So around Jupiter we have a couple of options here, a couple of moons, Europa and Ganymede, and around Saturn we have some moons, Enceladus, Dione, and also Titan. So we'll look at Titan next month, and we're going to have a look at Enceladus in a moment. We'll also look at Europa next month as well. So let's have a look at Enceladus now. This is actually a 3D model of Enceladus, which you can find online. They have quite a few neat free 3D models at the NASA website, if that's the kind of thing you're interested in. So Enceladus is one of Saturn's 82 known moons at the moment. And if you look up at the sky at the right time of year, in fact I think probably in the mornings at the moment, you can still see Jupiter fairly early in the morning. This is a night sky from Stellarium from earlier in May, where where Venus, Jupiter, Mars and Saturn were lined up, and I think that's what's still available in the mornings at the moment to see. So if you do see Saturn, its closest approach to Earth is going to be about 1.2 billion kilometres, which is about 67 minutes light travel time. Of course, it depends where Earth and Saturn are in the orbits, so that's the closest they'd get, but usually be further away. So when you look up at Saturn, you will not be able to see it, but you'll know that there is a moon called Enceladus, along with 81 other moons, but this one, Enceladus, this tiny little dot here, it's only about 500 kilometres across, which is pretty small, as you can see when you compare it to Earth and our moon as well. And it's actually 500 kilometres, you could plonk that on top of the North Island pretty much. This picture here, by the way, is called The Day the Earth Smiled, and it was taken by Cassini back in 2013, when they turned it to face towards Earth, which I think, that might be Earth in the distance there, Earth and Moon. And apparently if you knew it was happening, which I didn't, you were meant to stand up and smile and look in that direction. And so it was called The Day the Earth Smiled. And so the sun is behind Saturn, which gives this really neat picture. I think this is ring shine here, so the light reflecting off the rings shining back on Saturn. And this shows up some of the fainter rings that we don't generally see with the sun behind them. This is the E ring actually, which is actually that blue colour. It's quite an amazing colour. Now Enceladus here is the moon we're going to have a look at in a moment, but just out here is another moon called Dione, which is another icy moon. These two have managed to get themselves into what's called a 2-1 orbital resonance, and that means that for every orbit around Saturn that Dione does, Enceladus does exactly 2. So that means every, I think it's 33 hours, Enceladus takes about 33 hours to orbit. Every 33 hours they'll line up and give each other a little tug. And that means that the orbits can't remain exactly circular, which in turn means that they get a little bit closer and a little bit further away during the orbit, which changes the tidal forces on them, giving them a little stretch and squeeze, keeping the interiors warm. And so for Enceladus, it was found that there are actually some geysers appearing at the South Pole. Now this is, I think it was discovered in 2005, can't quite remember at the moment, but these geysers were seen by Cassini coming out of these stripes. These are called the tiger stripes at the South Pole of Enceladus. And these are actually creating this ring. So this is the E ring around Saturn, and it's produced or created by these geysers of ice, well, pretty much ice crystals by the time it gets out of Enceladus, forming that ring, which is actually pretty large. It's a lot thicker than the other rings and actually goes out a long way, I think almost to the orbit of Titan. And so it's a huge but very tenuous ring. So Cassini was able to fly through these geysers. It wasn't originally designed to do that, but when they found they were there, they changed a few things and got it to fly through. It was able to sample the geysers and the E-ring, since the E-ring comes from these. And Cassini found that along with the obvious water, well, I suppose it wasn't obvious, but with water there was sea salt, silicon and oxygen in the form of silicate, methane, organic molecules, both simple and complex organic molecules. There's carbon monoxide, carbon dioxide and hydrogen gas. Quite a lot happening there. So there's a lot of stuff coming out of Enceladus. Now it's quite possible that it might have just been a little pocket of water that the geysers were coming out of, or even some pocket just in the ice itself, which wouldn't have meant too much, but Cassini was able to do this thing called getting gravity measurements of Enceladus. So little tugs here and there will show slight differences in density in the inside of Enceladus. And altogether, in the end, it found that there must be a global ocean under the ice of Enceladus. And so that appeared to be the source of these geysers. So it was found pretty much that a global ocean must be present under the ice of Enceladus. And it was determined that the ice itself is probably between about 5 and 15 kilometres thick, but a lot thinner down on the South Pole where these geysers are coming out. The ocean itself is probably about 30 to 40 kilometres deep. Now, I mentioned that they found the sodium, so sea salt and silicate, coming out of the geysers. And these both mean, first of all, sea salt means that there must be an ocean of salt water, but the silicon and oxygen mean that the water must be in contact with the rocky core. And so what does that mean? Well, when we put it together with methane and hydrogen, you might remember earlier we talked about something that produces methane and hydrogen. That's the hydrothermal vents. In fact, the amount of hydrogen that was seen in the plumes was best explained by a hydrothermal vent system. So it's now certain that there are hydrothermal vents on the sea floor of Enceladus. So if we put that all together now, we can see that Enceladus appears to have these hydrothermal vents. Now you might sort of look at that and think those look way too big, someone's just drawn them and kind of exaggerated. But the gravity of Enceladus is only about less than 1% of Earth's gravity. And so these vents, or these chimneys, could actually grow to quite a few kilometres in height. So it's probably not too far out to imagine kilometre high or even a few kilometre high vent systems. And so now we have a place on Enceladus for life to get started. That's assuming that the hydrothermal vents are a way that life gets started. We kind of hope so, because obviously the surface pond idea is not going to work for icy worlds like this. So if that is where life gets started, then we have that option on Enceladus. And we saw our extremophiles earlier as well. We saw the halocryophiles, which are the microbes which are happy with very cold and very salty conditions. So what that means is we could probably take some of our halocryophiles and throw them into Titan. They'd probably happily live there. Radiophiles we saw, if they managed to crawl up to the top of the ice, they'd probably be quite happy with the radiation which would be present around Saturn. Cryophiles we mentioned before, living in the water, and thermophiles living around these hydrothermal vents. So Enceladus probably doesn't have a volcanic activity, so we probably wouldn't find the black and white smokers there as well. But we seem to have everything we need. The ocean itself is actually not that salty. I think it's determined to be only about 2%, so you probably don't even have to be a particularly extreme salt-loving microbe to live there. So that is definitely looking to be a habitable environment. For multicellular creatures, anything a bit bigger, it's likely or quite possible that Enceladus might actually be younger than the rest of the solar system. It may have formed only 1 billion or so years ago with a collision with something else. If that is the case, and it's only, say, 1 billion years old, if something did manage to form, it's well, it's possible, but less likely for anything larger to have appeared. And so if anything was there, maybe it's just going to be microbes. So it's habitable, but then we've got to remember that habitable doesn't mean inhabited, so we really have to go back and learn more to see if anything actually is living there. So that actually just about brings us to the end of the talk. And tonight we've asked the question, what is life? We've looked at life on Earth and the building blocks of life. And we've had a bit of a look at how life might get started and Earth's extremophiles. And then we finished off with Enceladus, having a look at one of the places which are habitable in the solar system. And so next month I'm going to have a look at Europa and Mars, Titan, some of the missions that are going to go out to Jupiter and Saturn, and other oceans in the solar system. And so that brings us to the end, and continue with part 2 next month. So I hope that's been informative and not too long tonight. Thank you. So questions, yes?
So would we consider tardigrades to be an extremophile?
That's interesting. I have heard that they call them not extremophiles, but they gave it another word, something that's extremely tolerant. So the extremophile, they like to generally say something that needs those conditions, but they say tardigrades may just be very tolerant and don't really need them. But then again, a lot of people call them extremophiles as well. So I guess in a way you could say that they can live in very extreme environments. So we definitely do have something that's more than just a microbe that is extremely hard.
Eukaryotes and multicellular, they're actually animals.
That's right, yeah. So that they're multicellular. It shows that life can come a long way, and it's not just the little things that are. So that's a good question, yeah.
I don't know if you've heard, and I can't remember where I heard it either. There was some sort of people were kind of spitballing about different types of life that you were talking about earlier.
Yeah.
Also talking about the kind of life that might form with nuclear chemistry instead of
Okay.
chemistry.
Yes, I have heard of that. I don't know much about it, but it's
sort of neutron styles.
yes, yeah. That would certainly be interesting. And when you think of viruses as maybe life, maybe not, then maybe we do have to define life a bit more than just, you know, the cellular way. So maybe there is something there, and it would be really interesting actually to see what further research comes out of that side of things.
It's really research at this stage.
No, well, I guess what research might occur that might give us some ideas here.
Anyone's interested, there's a science fiction story called Dragon's Egg
Okay.
by Robert Ford that introduces this idea.
Okay, yeah.
They're
Yeah.
tiny creatures that are about the same mass as a human, but only tiny because
Okay.
they
Very
live on
flat.
the surface. They're basically
Yeah.
made of nuclear matter,
Yeah.
and they operate by nuclear chemistry.
That would be interesting. Like I say, I don't know a lot about
It's
it,
an
but
interesting
yeah,
story.
interesting idea. Yeah, can't rule anything out though, can we? Really? Oh, Andrew.
What was the temperature of the Enceladus ocean or the Methane ocean?
Yeah, so for Enceladus, the water ocean would probably be a little bit less than 0. So water won't freeze under enough pressure, so you can actually have colder than 0 and still be liquid. And some of the other oceans, like we'll look at next month, for example, Titan may have an ocean under the surface which might be very cold but have a lot of ammonia and salt in it, which, like antifreeze, could actually keep liquid even colder still. So we can get some pretty cold liquid water.
I'm just amused by this terminology of these electrophobes eating electrons.
Yes, yeah.
Can you justify the word eating as opposed to absorbing?
Well,
I
I suppose when it comes to microbes, they really are always absorbing things, aren't they? So I guess we just call it eating or absorbing or breathing. Taking in, I guess, is probably the more scientific word.
Just checking.
Yeah, no, good question. Yeah.
Going back to the beginning, you were talking about the difficulty of deciding what counts as life. I would suggest that what unifies everything that any of us would consider to be life on that slide is the process that produced it. So it's the cumulative adaptation by natural selection. And the key to that is the replication, so the inheritance of some kind of genetic system, right? Some kind of genetic material, the DNA, in this case, and the ability to mutate and inherit those mutations. So, and you focused a lot on the cells, and those were really interesting systems for possibly creating cells. Are there any ideas, new ideas or interesting ideas about how that might have brought us that bridging step from these building blocks of things like DNA today to an actual genetic replicating chemical system? Because you need a chemical reaction that operates and tends to produce one of its starting components, but may make a mistake in doing so and have that be a heritable error. And then you've got life at that point. You will get evolution by natural selection.
That's right. I guess the thing is, like you say, it's there'll be a lot of mistakes made and things that just won't go any further. And I guess when you've got 1 billion years or so, it's just kind comes down to statistics. I can never say that word, statistics, as to whether it's going to actually happen. So yeah, but as
There was a paper came out recently claiming that life started on Earth more than 4 billion years ago, almost instantly when oceans appeared.
Yes, I have heard something.
They claimed that it was pretty much, well, in geological terms, instantaneous.
Yeah.
As soon as liquid was here, maybe 100 million years. So I think it's,
Yeah, so it may be very quick.
I don't think it's been reviewed yet.
No.
They claim from studies of ancient rocks.
And if that's true, that wouldn't it suggest maybe it came from somewhere else? That if the first evidence of life is very soon after Earth first became a livable place, it would be consistent with Earth then having been seeded.
Maybe Mars, yeah. Meteorites can come from Mars to Earth a lot more easily than Earth to Mars.
Or it's a very rapid evolution.
Yeah, so there's a lot to find out, but there's a lot of fascinating possibilities there, aren't there, really? Yeah. I think I missed part of my answer to your question, though, didn't I? Oh, you're asking about cells. How
the first steps to something like a genetic material system. You've got the pieces there, right? All
Yeah.
parts of the ribonucleic acid, but I just didn't know if there's any new ideas about how that got going, because to me that's the most important part, the genetic system.
It is, yeah. I guess there's a lot of ideas and research and people, well, I guess it's research, people trying to find different ways of getting things to happen, so.
A very basic question. We all know that life is carbon-based on Earth. What does it actually mean?
Carbon-based? So essentially carbon-based, we call organic molecules that have carbon, kind of a few carbon atoms and some hydrogen atoms as well. So the carbon-based means that carbon is the main atom that we'd use. If you thought of something like silicon-based life, it may not use carbon at all, but it's thought that it might actually react that easily and may not even be a great idea for life. And so one of the ideas is actually another thing called carbosilicon life, which again puts carbon in. And then there's the idea of hydrocarbon life maybe in the lakes on Titan. Again, carbon. So carbon just seems to be, because it's such a common atom, seems to be the one that seems to fit everything. As to why we call carbon life carbon-based and say Titan would be hydrocarbon-based, to me I guess it's carbon in the end, isn't it? Carbon-based life. But yeah, so silicon is the other one that people have talked about, and I think a couple of Star Trek episodes from way back used to have some living rocks which were silicon-based, life not as we know it kind of thing, but I don't know. It's another popular science fiction thing. I don't know if it's really has much chance if it's.
We've got the volume of carbon in our system that we are based on.
I guess it's because everything is kind of based on carbon in the end. So we kind of like when you look at all those molecules before, like the we've got the nuclear bases. They've all got carbon in their molecules.
You spoke earlier on about how the molecules have all been created around what elements are available, basically. In any asteroids or meteorites that have fallen to Earth, have they ever discovered elements that don't exist on Earth?
So what they actually did find, and they're not sure if I think they're still looking to see if this is correct, but they thought they'd found a protein, was it hemolythin, which actually still had carbon, but it had some lithium and some iron in it. So it was a protein that had kind of been created or formed in space, not used by anything on Earth, possibly not used anywhere, but kind of showed that proteins of other types could form. So the actual elements themselves, I think we are aware of all of them on Earth now. So I don't think there'd be any other elements, the atom types that have been found.
Out of space, we don't think.
I think we pretty much found them all and made some more in the labs, which are not naturally occurring. Yeah, so pretty much the same atoms all through the universe.
Therefore, all the molecules that we've discovered should be very...
So that's the thing, yeah, that's why it should be... in fact, some of the molecular clouds, the interstellar molecular clouds, they've found various atoms. There's that one molecules, the one called ethanolamine, which is used in the lipids they found in a molecular cloud way out, interstellar molecular cloud. So it sort of gives the idea now it must be everywhere, these kind of things. So life may be, even maybe Earth-type life might be everywhere. I mean, that's a guess, who knows, but...
I was just going to say, there's another step, theoretical step, is that you have to get to a DNA system somehow. DNA is quite a complex mechanism. You've got special enzymes that transcribe it and things like that, and then use the transcription to produce proteins. So you have to have some way of getting to that. It's obvious there's got to be some kind of intermediate step.
That's right, it's kind of a missing
call
step.
It the RNA world.
That's right, yeah.
Supposedly RNA can catalyse some of these things itself.
Yeah.
So, and then you have sort of a DNA takeover
I think
at some
so.
point. That's one of the more popular ideas at the moment.
So somewhere along the line it just kind of managed to create that DNA molecule, yeah. A lot of mystery still there, a lot to be solved. Any other questions?
No questions from online, but there was a comment from Mike who says, note that our red blood cells don't have a cell nucleus or DNA, so that complicates things.
Probably does, yeah, it makes things more complicated, but I think you probably have to start with the cells with the cell nucleus to start with, and the red blood cell would just be a later on kind of a thing.
Well, they don't replicate though.
They don't.
The bone marrow.
That's, yeah.
The production of them loses the nucleus.
Yeah, that's true. Yeah, for a replicating one, you need the. Yeah. Good point. Though. Right. No other questions. Oh, thanks. Anyway, thanks very much.
Thank you very much.